So one of the first optimizations we're going to look at is what we call vector chaining. So vector chaining, introduced in the Cray 1. The idea is that you don't have to wait for the first operation to complete, or the whole vector to complete, before you start the second vector. Because if we went back and looked at this picture here, this load creates the element of the vector 0, we'll say. This operation here looks at the third element of the vector. So it cannot execute after this load is done. It has to wait for this one. But this multiply here can execute right after this load happens. So chaining in vector architectures is to some extent the moral equivalent of register bypassing. And what this looks like is first of all, you don't actually have to add intra-functional unit bypassing. The most basic notion of chaining is you bypass just between functional units. So what will happen here is we can actually do a load, and we can take the value of the load as it's heading for the vector register file, and also sort of feed it in through our bypass network into a different pipeline. So for instance, the multiply pipeline in our example that we've been looking at. And you can take the result of the multiply when it's done and feed that into the like store pipeline or something like that if you have a broken apart store pipeline. Or in this example here, we're actually feeding a multiply into an add. So the advantage here is, as I said, instead of having to wait for load, multiply, and the next instruction, and wait for them to complete, we can actually overlap portions, subportions of the dependent instruction when they become available. So let's look at how this works out here, where we're doing chaining, but through the register file. So chaining through the register file, what I mean by that is we're not going to have a bypass directly from the output here to the read stage. We're actually going to have to wait for it to write and then read it, but at least we can overlap. In our previous example, we were not even able to do this overlap. We had to wait for the entire register to, or vector register to be written. So we effectively pulled this forward from here to there. But what you might notice here is, well, this value is already here, so we can even try to pull it a little bit farther forward by actually adding bypassing, or more traditional bypassing. But this is just chaining through the register file. OK, so now let's add chaining through the bypass network. And it didn't change. Well, what happened? That's a bummer. Nothing happened. I was expecting this to go faster. You know, I want to make my architecture go faster here. Well, what happens is these R's, you start to get structural hazards on the read port of the vector register file. So to make this go faster, we're actually going to have to add more read ports and more write ports to the register file. And if we were smart, into the vector register file, if we were smart, what we really want to do is we want to add one per pipeline, or basically as many as we need ports per pipeline. So if you have 2 input operands and 1 output operand per pipeline, you're probably going to add 1 output operand and 2 input operands, or 2 read ports to your register file and 1 write port to your register file per pipeline. And this actually lets things go execute faster. So now we have bypassing, and we have more register file bandwidth. So more ports to our vector register file. So what you'll note here is now we have multiple things in R at the same time, multiple things in W at the same time. And we can do that because we have multiple ports to our, multiple read ports and multiple write ports to our vector register file. And the other thing you should note here is this multiply here, which is on element 0, needs the result here of the load And it gets created here and gets bypassed down to here, and then just goes and executes. And then they just step in lock sequence here. And similarly, the store here needs the output of the multiply in Y3 of the first element, so it can bypass it there and then start doing the store. So we're able to get some parallelism here, even without having multiple copies of the same execution unit. But we are able to get parallelism in our vector architecture. And what's really cool is we only had to issue 3 instructions to do this. So very low instruction bandwidth. And I wanted to make the point here that this is a kind of a contrived case, because our vector length is very short. It almost doesn't make sense to actually use vector instructions to do this. But here is a picture of the same sort of thing happening in the overlap you can get when you increase your vector length. So here we're going to set our vector length register to 8, and we're going to get much more overlap of the executions of this. And you can basically have this instruction here starting the element 0 operation here starting 3 cycles after that first load. And this would be as if you had, let's say, 8 independent scalar processors sort of running in parallel. But we could do with almost no encoding space. So questions about that so far? A little technical with the pictures. Lots of bypassing happening here through the bypass network. But the bypassing is relatively restricted. We only need to bypass one value at a time from one location to another location. We don't. And if you do it through the register file, it only sort of pushes this out one cycle, so it's not so bad. Or pushes each bypass out one cycle. OK, so this brings up the question, what happens if your vector length, or the size of your array, does not equal a nice power of 2 multiple of the vector length register? Or let's say the vector that you're trying to multiply is much, much larger than the maximum vector length register can be. So we introduced this notion of strip mining. And the idea is that you do big chunks, and then you do the remainder by resetting the vector length register. Now, you can either do this one of 2 ways. You can either do the remainder first and then do the big chunks, or you can do the big chunks and then do the remainder. And both our designs have actually been used. To some extent, this is a software technique here, because the architecture just allows you to set the vector length, but doesn't have any special hardware to support this. So if we look at a piece of code here, this added a lot of stuff to our loop. Now, all of a sudden, we still have load, multiply, store. This is our old instructions that we had before. But we have all this other stuff here. It's sort of bumping pointers, comes back into it. And we also have to write the vector length register every single time through this loop. And the reason we're writing the vector length register here is we're going to write it with this is actually coded right now that we do the remainder first and then do the big chunks. So we're going to write the vector length register with the remainder first, so n mod 64. Do that chunk first, and then we're going to do the rest of them with 64. What I really want everyone to take away from this is when you actually have to do strip mining and you know that the array size is not a nice even multiple of the vector length, you actually have to do more work here. You have to do more work in your loop. The other thing I want everyone to take away here is the vector length register allows you to do this, but you actually have to change it. You can't just set it to one value. So let's look at a code example here. Oh, yeah, I wanted to say a lot of this stuff here is overhead. It's sort of extra overhead. And for short vector lengths, this can be a problem. For longer vector lengths, this starts to go away. So here we have vector strip mining. And we have a same piece of code that we saw before, but now we sort of have to load, mul, store, and then we have just some junk down here. And this junk is that extra code you need to basically handle the loop around and the checking and the bumping of pointers, and to be able to handle that n may not be a fixed number. One other thing I wanted to point out about vector strip mining is this allows you to handle variable length arrays that you don't know at compile time also. Because you can just use n here, and this code snippet will do the right thing. One other thing I wanted to point out here, I didn't draw this because this is actually very hard to draw and it wouldn't fit in the slide, is this overhead is substantial when looking at a small vector length like 4. If we make our vector length 64, there's a lot more work up here, and this sort of starts to be small and unimportant to some extent. So this is the overhead of this loop checking, and then the maintenance of the loop. It starts to get small when you have very long vectors. OK, so now we're going to start to look at parallelism a little bit more deeply. So here we have an instruction. We have a deep pipeline ALU, and we're going to have multiple things flowing down the pipe at a time, multiple results. And we're going to take A of 3 and B of 3, and it's going to take 6 cycles to do this multiply. And this is assuming that we have one pipeline functional unit. But what if all of a sudden we started to have multiple copies of the same functional unit? Well, we can actually start to think about executing these things in parallel and interleaving the respective operations. So we have results C of 0 here, C of 1 here, C of 2 here, C of 3, and then modulo around it, it wraps around. So this is effectively going to decrease our chime because we're going to add more functional units, more parallel functional units, more copies of the same functional unit, and that allows us to speed up our execution. So here is an example of that same architecture we were looking at, but now instead of having one copy of everything, we have 2 copies. And typically these things are called lanes. So we're going to call this lane 1 and this lane 2. And take a look at the same piece of code of this vector strip mine loop with a vector length of 4 with 2 lanes. And what you can see is this basically pulls forward, and we can overlap multiple loads at the same time. So 2 things are in L0. And also in this multiply here, we can have basically 2 multiplies going down the pipe at the same time, like that. Now, one thing to note here is different architectures can do the interleaving in different ways. This is one possible way to do the interleaving. You could also think about having these 2 pulled forward and these 2 delayed or something like that. Both of those architectures work. But I will say that typically you'll try to interleave your lanes in a low order interleaved manner. So what that would mean is not this picture. This is a sort of higher order interleaved manner. But a low order interleaved manner would be elements 0, elements 1, element 2, and then you, or 0, 1, 2, 3, and then you wrap around. This is a picture here showing an architecture which has 4 lanes. And one of the things I wanted to just point out here is you can actually partition your register file from an architectural perspective, from a hardware perspective. You don't need to have one monolithic register file because you know that you will only ever access, let's say, element 0, 4, 8, ... of your vector registers. Or excuse me, this is elements of the vector register. So if you have a 64 elements in your vector register, elements 0, 4, 8 of those can go here. So you're basically doing interleaving of the respective subportions of a vector register across these different lanes. So you can partition the register file is the key takeaway point here. I drew this to sort of show two different things going on. Let's say like in our examples we've been looking at, one of these is the multiply pipe, one of these is the add pipe, and here we have our load store pipe or something like that. So you can have multiple things in a lane. And then, functional unit sort of runs the other way. So this is all of the adder units, we'll say. And in fact, this is basically exactly the architecture of the T0 vector processor from Berkeley. And as you can actually see their layout here, they striped over the lanes the respective elements of one register in the vector register file. And then they actually mirrored the data path here. They actually have two copies of the same thing on either side of the lane. And then up here is their scalar processor, their control processor, if you will. And this is where they execute the scalar operations, like the shifts and the branches and things like that. OK, so to recap here, vector instruction sets have quite a few advantages. Main one is they're very compact. One instruction can generate lots and lots of work to do. And they're relatively expressive. What I mean by expressive is that they very concisely say exactly all the constraints between all the different operations they generate. So for instance, each of the different operations are independent. This allows us to stripe the registers. It allows us to know that we don't need to bypass. It allows us to sort of access all these registers in a striped manner in a disjoint way. Our memory pattern, at least for unit stride operations, is very well understood and very easy to plan for. We know that it's going to bank very well. So if we have a cache, for instance, we can actually bank our cache because we know if we're doing unit stride operations and we have multiple lanes, for instance here, we know that we're only going to be accessing the 0th element of a vector here, the first element there, the second element there, et cetera. And this works out very well from a banking perspective, but sometimes it may not always work out. And finally, these sorts of architectures can be scalable. And what I mean by scalable is you can add more lanes. And as long as you don't add more lanes than your maximum vector length, you're probably doing OK. Or you might want to be off by a little bit, your depth of your pipeline. But you can add more and more work. And in fact, people actually build families of these processors where they have different numbers of lanes in the same architecture. And this is actually common in our GPUs today, where they will have multiple copies of the same unit, and they'll actually build different variants of the same processor pipe, or same pipe processor pipeline, where you'll have ones that have, let's say, one lane versus, 15 lanes or something like that. And you can sell a high-end part which has 15 lanes and a low-end part that has 1 lane.